Okay, today we are going to look at problem number 18 from the free response packet. Let's see what we got. So we have this table with a bunch of different information. It's a table of f. Let's see. So all about f. Let f be the function that is continuous. That's going to be important. So it's continuous on the interval. The function f is twice differentiable except at x equals 2. So at x equals 2, it's not twice differentiable. The function f and its derivative have the properties indicated in the table, where d and e indicates that the derivative does not exist. So at d and e, so it does not exist here and here. Okie dokie. Looks good so far. What do we got to do? For x equals from 0 to 4, find all the values for which f has a relative extremum. Determine whether f has a relative maximum or relative minimum, then justify. Okay, so let's see. We want to find a relative extremum. So relative extremums, so relative minimums, relative maximums. Let's think about where they occur. They occur at critical values, and critical values occur when the derivative equals 0 or when the derivative is undefined. In other words, the derivative does not exist, d and e. So let's see what we got here. So I think you would agree, looking at our thing. So let's go back to our table, and I'm going to kind of erase some of my highlights here. We want to look and see where does a derivative equal 0 or where does it not exist? And I think you'd agree it equals 0 here and it doesn't exist here. So these are my possible critical numbers. So those are the numbers that I'm going to be testing. So I'm going to make a sign chart for my function here. And I'm going to put in my critical numbers. So I have a critical number at 1 and I have a critical number at 2, right? Because when x equals 1, the derivative is 0. When x equals 2, the derivative does not exist. To the left of 1, we can see that the derivative is positive. To the right of 1, it's also positive. So what does that tell us? That tells us that there is a stall point at x equals 1. So there's not a relative maximum, there's not a relative minimum. Let's look at x equals 2. So it does not exist there. And then to the left of 2, it's positive, which we've already indicated. To the right of 2, it's negative. So this means there has to be a maximum at x equals 2. Okay, so I think we're ready to go and state that. So we can say let's see how we want to say this. So I'm going to say, let's type this. So I'm going to say f, it's kind of weird. It's the function f has a maximum at x equals 2 because, let's see, when x is less than 2, right, f prime is positive. And when x is greater than 2, f prime is negative. Okay? Let's make sure I said that correctly. So we said that the function has a maximum at x equals 2, which we said, and the reason was when x is less than 2, it's positive, that's correct. And when x is greater than 2, it is negative. Perfect. Perfect, 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 except let's blow it up just to make sure you guys can see that okay. Maybe I can't blow it up. Come on, come on. There we are. Boom, 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 boom. Okay. Let's keep on going. So that's letter A, right? I think there was anything left in the letter A. Determine what? Nope. Perfect, perfect, perfect. Let's move on to letter B. Okay, so letter B, we are asked to graph the function. I'm going to redraw that. That's really small. But before I do, let's think of, so what do we normally do when we graph a function? Well, we go find the points, right? We plot some points on our coordinate grid, and we make sign charts. So I'm going to go through and make sign charts. I've already got some points, so I'll take care of that later. So let's go make some sign charts. And I'm just going to kind of include every number that they've kind of got on my table here. So I'm going to include the number 0, 1, 2, 3, 4 on there just to go through and do that. So 0, 1, 2, 3, 4. And let's go back to our table. So looking at that, so now this is going to be, I'm going to call this function on this table, that's f prime. Okay, so this is going to be the sign chart for f prime. So we notice from 0 to 1, it is positive. From 1 to 2, it is positive. Again, remember we said there's a stall there, so we're going to have to indicate that. From 2 to 3, so from 2 to 3, it's negative. From 3 to 4, it's negative. Okay, now let's go do the same thing for the second derivative. And I'm just going to, again, use the same numbers here just to be consistent. Quick reminder, sign charts. I know this isn't an explanation one, but you would not be able to use sign charts for your explanation. Okay, so let's see what we got for our second derivative. From 0 to 1, it is negative. From 1 to 2, it is positive. From 2 to 3, it is negative. From 3 to 4, it is positive. Looks good. Looks good. I like it. Okay, let's see what we got here. Let's go make a graph, shall we? So I'm going to kind of do this. And what did they say? It goes from 0, so 0, 1, 2, 3, 4, boom, boom. Okay, let's see what we got. So we were given some points, right? So we were given some points. So we were given the point 0, negative 1. I'm going to graph this whole thing in purple. So we're given the point 0, negative 1. We were also given the point 1, 0. And boy, this is kind of a pain. 2, 2. And 3, 0. And then finally, they did not give us anything at 4. Okay, but they did tell us that it's going to go negative. Okay, good times, good stuff. Let's see what we can do here. So according to our first derivative, right, from 0 all the way to this thing is increasing. Looking at our second derivative, though, we notice that from 0 to 1, right, from 0 to 1, that it is concave, it's negative, so it's concave down. So I'm going to make that kind of extreme. Also, since there's a stall at 1, I'm going to really kind of emphasize that stall at 1. So notice how my thing just kind of stalls there for a second. It gets a derivative of, it gets that slope of the tangent line 0. And then what does it do? From 1 to 2, it is concave up. So it looks like this. But notice, we know that at 2, it's they told us it's not differentiable, so I'm going to want to make sure there's like a cusp or something going on there. So something maybe like this. Then from 2 to 3, it's the derivative says it's negative, which makes sense, but it's also going to be concave down. So I'm going to emphasize that, concave down. Okay, then from 3 to 4, according to our derivative chart, it's going to continue decreasing, but it's going to be concave up. So something like that. Okay? Looks good. Looks good. Let's keep on going. Let's move on to letter C. I'm going to probably do a couple things here. I'm going to grab a couple things just so I have some more space. So let's go and grab the table. I'm going to move that down here. And I'm going to grab letter C so that I can see it. Perfect. Okay, what do we got here? So we're on letter C. Let G be the function defined by g of x equals that stuff on the open interval from 0 to 4. For 0 to 4, find all the values of x at which g has a relative extrema, so kind of similar to what we did with A. Determine whether g has a relative maximum or a relative minimum of each of these values. Justify your answer. Okay, so we're going to do something similar. So we're told that g of x equals this. And of course, because we are going to look for extrema, I've got to take the derivative. So in other words, g prime of x is going to be equal, by the second fundamental theorem of calculus, is going to be equal to f of x. So now I'm going to be looking at, let's highlight it in orange. I'm going to be looking at this line. This is now the derivative of g. That line right there is my derivative of g. And I'm going to be using it to analyze my stuff. So critical numbers. Let's find where our critical numbers are for this one. So critical numbers occur, again, when the derivative equals 0 or where it's undefined. So what do we got? Let's do it in pink. So we have a critical number at x equals 1. We also have a critical number when x equals 3. That's it. Those are my only two ones. Remember, this function is continuous. They told us f of x is continuous, so there's no, we don't have any issues. Those are our only two issues that we have. So x equals 0, so x equals 1, and x equals 3 are two critical numbers. Now, let's see what's going on for these. Let's see what's going on for these. Let's go make a sign chart, as always. So my sign chart for g prime of x, which equals f of x. Again, sign charts, they don't look at them, so this kind of me being super precise here doesn't matter, but I like to be precise anyway. So this is the point 1, 0. Sorry, we have a critical number at 1, we have a critical number at 3. Critical number at 1, critical number at 3. What do we have? To the left of 1, it's negative. To the right of 1, it's positive. And to the left of 3, it's positive. To the right of 3, it's negative. So we have a minimum here and a maximum there. So let's do it. Let's put this together since we were asked to justify it. And let's get the size of our font good from the start. So I'm going to say, let's see, because g prime equals f of x. So again, I'm pointing, so it's because g prime equals f, right? I'm saying I'm looking at the derivative of g. How am I doing it? I'm looking at g prime. I'm looking at g prime by looking at the function f. So because g prime equals f equals 0 at x equals, what was it? X equals 1 and x equals 3. We have two critical points to examine. So at x equals 1, there is a relative minimum because, and I'm just gonna kind of reiterate this. I don't know why, but so because g prime equals f of f is negative when x is less than 1 and positive when x is greater than 1, right? So I'm showing that it changed signs. So it changes from negative to positive. So it's negative when x equals 1 and positive when x is greater than 1. And did I say that there was a minimum? I did. I did say it's minimum. Next, at x equals 3, there is a relative maximum because, and I'm just going to reiterate, I'm just going to repeat myself again, g prime equals f, because g prime equals f, let's see, how did I say it before? Because, let's see. Yeah, I'll kind of do the same thing, is positive Did I spell it right? Yep. Positive when x is less than 3 and negative when x is greater than 3. Perfect. Perfect, perfect, perfect. Though kind of sloppy English, but whatever. This is not an English class. So let's just make sure before I continue there. So I wanted to basically show that it changed signs at x equals 1 and x equals 3. And in this case, so at x equals 1, I said there was a relative minimum because it went from negative to positive. That's correct. And then at x equals 3, there's a relative maximum because it went from positive to negative at 3. Perfect, perfect, perfect. Okay, let's move on to letter D. Letter D. Let's go grab letter D. Oof. Okay. So actually, you know what? I might need that table one more time. Or maybe I can get by with it. Let's see. For the function g defined in part C, okay, find all the values of x from 0 to 4 at which the graph has an inflection point. Okay, or inflection points. So let's think about inflection points. So inflection points occur, we're looking at the second derivative, and we're looking at where the concavity changes sign. So it changes from positive, negative, negative, positive. Okay, so in this case, what I'm going to say is I'm going to be looking at the second derivative of g. So I'm going to say g double prime. So remember, we said that g prime equaled f of x. So I'm going to now say g double prime of x equals f prime of x. So now, looking back at our table, let's clean this up for a second. Wait, why didn't that? Yeah, there we go. Now I am looking at this line right here, right? Because that's going to be the second derivative of g. And I'm doing the same thing as I did before. I'm looking, where is it? Where does that second derivative equal 0, or where does it not exist? And I think you'd agree there are two key pieces, and our two key pieces occur when x, let's see, we got our two pieces that we want to look at are here and here. But let's just kind of look at our chart really quickly. I'm not going to make a sign chart on this one because it's fairly easy. Look what happens when to the left and right of 0. When x is less than 0, f prime is positive. When x is greater than 0, x prime is still positive. Sorry, f prime is still positive, which means, right, that the concavity for g is concave up to the left and to the right. So there's no inflection point at x equals 0. But when we look at x equals 2, to the left of x equals 2, f prime is positive, and to the right, it's negative, right? So g is concave up to the left of 2 and concave down to the right of 2. So it changed concavity. Therefore, at x equals 2, we have an inflection point. So I know that was kind of rough, but let's see if we can put that together. So I've already shown, right? I've already shown that I'm using g double prime to look at f. I'm looking at f prime to look at g double prime. So let's say the following. So at x equals 2, there is an inflection point. Because, and this is, I'm going to point one more time. I'm going to say because g double prime equals f prime, and when x is less than 2, g double prime of x is greater than 0, and when x is greater than 2, g double prime is less than 0. Let's make sure I set the die show. It does change sign, and it did it correctly, I believe. Went from positive to negative, went from positive to negative. Perfect. So there's an inflection point. How do I know? Because the concavity changed. Okay, so that is all there is to that one today. Again, as always, if you have any further questions on that, please feel free to ask them during the Zoom meeting that we are going to have either Tuesday or Wednesday, depending on your period. I will see you then. Again, if you have a question. If not, then I won't see you then. So, as always, please make sure to do not like, comment, or subscribe. And I will talk to you later.